Okay, this video is about the application of integration and to talk about how to find the area under the curve. Okay, hopefully you know a lot about derivatives and how they show the gradient or the slope at any point. The integration gives us the area under the curve. Now, you don't get the area at a point, you get the area between two x values. So you have to have a starting and a finishing point. And when we say area under the curve, that's area between the curve and the x-axis. Let's have a look at it. Here's a notation. That's your integration symbol. That's your lower limit and that's your upper limit. Lower limit means the left-hand side of the graph. Okay, and upper limit is the right-hand end of the area. The thing you're integrating, or your function, is called the integrand, and your x dx is your variable of integration. You don't hear anyone use the word integrand, but there it is for you. Do not leave off the dx. It's really important to show that you're integrating with respect to x, as long as it is x. If it's a function of t, then you do dt or whatever. Okay, the area under the curve is given by that formula, the one we just looked at. When you do this, you get, see the small f here and the big F here? So the capital letter F is your antiderivative. And you get the antiderivative and you substitute in b, and then subtract antiderivative with a substituted in. I'll show you how this works in a second. By the way, this is also called the fundamental theorem of calculus, and it's really interesting to investigate that and see how that works, which we'll probably do at a later stage. We're going to do a couple of easy examples. Here's the easiest example of them all. There's our curve in inverted commas. It's a straight line, a horizontal line. Okay, I want to find the area under that curve between x equals 2 and x equals 6. So that's my formula. Now, y equals 6, so I put that in. We take the antiderivative of 6. That's 6x, of course. Change my format here. See, now I've got a still between 2 and 6, but I've integrated, so I don't have the integral sign anymore. I have square brackets. Now I substitute in 6 and 2. So 6 times 6, your upper limit, minus 6 times 2, your lower limit. It's 24. This is a rectangle, so obviously I can check the area. It's 6 by 4, 24. Hey, it works, I got it right. Awesome. Let's do something a little bit more sophisticated. Here's another straight line. This one's oblique. I want to get the area, that area, between x equals 1 and x equals 4, under the curve, or between the curve and the x-axis. Okay, there's my formula. I substitute in y. I use 3 on 2 here instead of 1.5, but same difference. Okay, take the antiderivative of this. Okay, the x integrates to x squared over 2, so 3 on 2 becomes 3 on 4. And 2, the integral is 2x, or the antiderivative is 2x, and our limits are 4 and 1. Now we apply those limits, substitute in 4, and then minus, substitute in 1, and you get 17.25. Okay, this shape is a trapezium, or a trapezoid if you're American. Okay, a trapezium, so the area of that is a half 3.5 plus 8 times 3, 17.25. Hey, it works. So now with something like this, there's our function, there's our area, again between 1 and 4. I know that this is going to tell me the area because it's worked with the other two. Okay, put in the value of y, take the antiderivative. Okay, x squared becomes 1/3 x cubed, 3x becomes 3x squared over 2, 5 becomes 5x. Substitute in 4 and 1 as your limits. 13.5 is the answer. Cool. Here's one you can try. Once you pause the video, try it and come back in a second. Okay, here's the answer. The area is going to be the integral between 1 and 2 of x squared dx. The antiderivative of x squared is 3x over 3. Substitute in 2 and 1. Subtract. 7 over 3. It's 2 and 1/3. If you think about it, that length is 1. If I kind of chop that there and make that a rectangle, it's going to be about there, which is just over 2. So yeah, 2 times 1, the area of that, yeah, is 2 1/3. Cool. This is where it gets a bit complicated. You've got a negative area down here and a positive area up here. If I want to find the area, I want the absolute value of all of this. I don't care if it's negative or positive, I want to know how big is it when I'm asking find the area. Find the integral, something different. Find the area, I want to know what is the actual size of that. Okay, so what I've got to do is for this area from -1 to 1, x value is -1, it's going to be a negative area, so I've got to negate it. Negative times negative is positive. So now the answer here, and then I add it to the area between 1 and 2. So the answer here is going to be all positive, and that's going to be the actual physical area that's involved. Okay, I put in the formula for y, the equation for y, formula. Okay, take the antiderivative. It's going to be the same for both of them because it's the same curve. And then now I've got to apply all the limits. There's no shortcuts here, right? Take it step by step, write everything down with the negatives and the positives and the minuses here. It's going to be really complicated, easy to make a mistake. So take it step by step and work each bit out and then add them together. 10 and a 6 is the answer. Okay, I want to show you something on my calculator. This is exactly the same function. I'm using a TI Nspire calculator. First I would draw the function like this, so I could see where it crosses the x-axis. I can solve for that point. Okay, so now I know where to set my limits. If I took the integral just between -1 and 2, I'd get -4.5. And that's not the area, because that's adding this big negative area to the small positive area, and so big negative plus small positive is still negative. Okay, so that's not going to tell me the actual area. You have to think about it. If you want the actual area, you've got to negate the negative bits and add them to the positive bits, and then you get 10 and a 6th. Okay, so TI Nspire is a good investment because it can do all this for you. Other calculators can do it too. Just doesn't look quite as fancy when you do it on the other ones. Okay, one more example. This is finding the area between the x-axis and the curve y equals cos x from x equals 0 to x equals 3 pi over 2 radians. Okay, first thing to do, draw the diagram. And you can see here you've got a positive area and a negative area. Okay, just checking on my region. X equals 0 is there, x equals 3 pi over 2 is there. And where does this 0 here, what's that? That's pi over 2. Okay, this is stuff you know, alright? 0 degrees, 90 degrees, 180 degrees, 270 degrees. Right, you know that cos is 0 at 90 and 270. Just as a reminder, the derivative of sine is cos, so the integral of cos is sine. Simple as that. we've got indefinite integral here, so it doesn't have any limits, so I've got a plus c. When we do it, we won't have the plus c's, of course, because we'll have limits. So to get the actual area, this whole shaded bit, nice pink color there, the whole shaded bit, I don't care if it's negative or positive, I want just the total measurement of the area. So we've got the positive area from 0 to pi and 2 minus the negative area, so minus negative means plus, between pi and 2 and 3 pi and 2. Okay, same equation because it's the same curve. Take the antiderivative, of course it'll be the same because it's the same curve, and now we just need to apply our limits. Okay, again, no shortcuts here, work it all out. Sine of 90 degrees is 1, sine of 0 is 0, etc. And you've got all those values there. Works out to give you 3. Okay, I hope this gives you a good idea about working out the area under the curve. These are all pretty simple examples, but they tell you everything you need to know, and you can just apply it to more difficult examples in the same way. Alright, good luck.